All right, so let me introduce Willem Schreuder. He is, I'll let you introduce yourself, Willem, but yeah, he is one of the gurus behind RMHAM. Okay, cool.
So
Switch over here.
I decided to be brave today, and I'm going to try to do most things live. So maybe we should turn the lights back on again so you can see me, because I'm going to try to do things here. Good morning. Thank you all for coming. My name is Willem Schreuder, ACØKQ. I am the Director of Continuing Education at RMHAM, so I am to blame for RMHAM University and things like that. RMHAM, of course, is an ARRL special service club, so our mission is basically to provide support for other clubs. You can join RMHAM by paying dues. The only way you get in is with sweat equity. So the idea is that if you participate, am I not sharing?
Yeah, if you just hit the share button again.
So the important thing is that what we're looking for is participation. So to the extent that you can come and participate in one of our trips out to a repeater site to do maintenance, or participate in network operations, or one of those, that's basically how we pay our dues. I should also remind you that we're a 501c3, so on Colorado Gives Days, please consider RMHAM when you're making all of your tax-deductible donations. But basically, we have a very strong emphasis on providing emergency service. So the purpose of the backbone, to some extent, is to provide backups to a lot of the public safety agencies that we have points of presence in the emergency operations centers. So if the commercial service goes down, you can file over to that. And our DMR network is specifically designed with public safety in mind. So there are dedicated talk groups for various areas that we can then provision for that. Of course, what we're most known for is the RMHAM backbone, and what we have over here is a little model of about a tenth of the overall network. So the overall network comprises about 250 sites. Here I've got 31 of them. But we have cooperating agreements with a bunch of other organizations, the Colorado Connection, the CRA, LARC, NCARC, and various other groups, that basically we provide the backbone infrastructure to connect all of the repeaters together. And of course, the RMHAM DMR network is basically how we provide the DMR repeaters for the East, Central, South, and North groups. And then, of course, the other thing that we do is RMHAM University. RMHAM University is basically a morning-long class on some technical topic. And then we have one last month on DMR. We've got one on direction finding this month, and so forth. So to the extent that you want to participate in those, rmham.org is a good resource. My favorite RMHAM is the one we hold in February, which is called NA0TC. So the idea is there that you give about a 20-minute talk on some nerdy topic that doesn't fit anywhere else. So it's kind of a fun activity. So basically, the backbone is the microwave network that we use to tie all of these sites together. It's based on IPv4, so the Internet Protocol version 4. The nice thing about IP is that it's a universal transport mechanism. So not only can you move audio, you can move data, you can move telemetry, we can use it for command and control. It basically allows us to connect to everything. So it's a very powerful mechanism for linking all of the sites, primarily because it's very robust and it's redundant. So it's not reliant on any individual link. If you have failures in the system, built into IP is a way of routing around those kind of problems. So it makes life a lot easier if the software that you could get with the various pieces of equipment natively supports this stuff and you don't have to hack on it a lot. So mostly what we use is commercial 5 gig and 60 gig gear that are geared towards the internet service provider, the wireless internet service provider data in particular. The nice thing about the 5 gigahertz band is that we actually have a ham band right next to the commercial or ISM band. And so we can actually use the equipment from the ISM band and just run it on amateur radio frequencies and have a much quieter environment. And of course, at all of the sites, all of your equipment needs to be IP enabled in order to be able to use it. So a lot of the modern digital modes, that's inherently part of it. But then for older analog repeaters, we basically use the old Starlink technology to link all of the repeaters together. But you also have the ability to control power equipment, the solar controllers, at sites where we have security. We can have cameras or door entry controllers. We can use VoIP phones at the sites where cell phones don't work. It's just a really convenient way of putting this all together. So this is where the wheels come off. Here's where I need to start showing things in real time. So basically, the applications that we need to use are the ones that are shown here. But how does it all come together? So this model here has 32 routers on it. This one over here, I use to pretend to be the internet per se, right? It's all of the commercial internet locations. And each of the routers here represents one of the sites. So our backbone sites are shown down here in the middle. So backbone from Buckhorn down to Fremont. And then all of the sites are all of the parts that go in various other directions. Each of these routers are basically a little Linux computer that is sold by a company called Microtech. And what they are basically doing is adding some switching chips to make the switching a little bit faster. But it's basically just a Linux computer that then does all of the routing. And most of the equipment that we use are these Microtech radios, as well as the Microtech routers. The advantage of using Microtechs is you get the same functionalities you get out of the Cisco, but between 1/10 and 100th of the price that you would pay for a Cisco. So what this represents with all of these purple wires are actually microwave links. So all of these purple wires you see all over the board represent something that is typically got one of these on one side or the other. So this is just a 2-foot high gain antenna. This one is particularly for 5 gigahertz. And it's a 30-something dB gain antenna. And then on the back of it, we've got one of these net metal radios. So I didn't power this up because some of you may still want to have children. But this is basically a 2-watt radio. At the bottom, you can open it up. The nice thing about these is there's no loose parts on this. So if you're up on a tower, nothing is going to drop. There's a lot of swearing involved, but at least it's not going to fall all the way down. But at the bottom here, we've got an Ethernet jack and an SFP cage. And basically, you feed power to the radio through power over internet, right? So you've got 8 pairs in the Ethernet wire, 4 of them are used for power, and 2 of them are used for data. It's a 1 gigabit connection down to the router or whatever is at the bottom. And then at the top here, I'm not going to disassemble it, but there's a couple of SMA connectors, which you then connect to the actual feed horn on the radio or on the antenna using these short coax jumpers. And so basically, this is a completely self-contained unit. You put IP in one side, and you get RF out the other side. And the radios in the 5 gigahertz band kind of tune somewhere between about 5 gigahertz and just over 6 gigahertz if you buy the international version. So the radios themselves are obviously capable of significantly or spectrum, but they are firmware controlled. If you buy the US version, you can only use the frequencies that are in the ISM band in the US, and you can, of course, buy it for other countries as well. If you buy the international version, there's a way that you can go in the standard configuration without having to screw with the firmware to actually set those in the ham band, which is what we do in most locations. Of course, depending on where you are, running this just in the ISM band is also not a problem because it's really RF quiet. But if you're at a site like Thornton Mountain, where you can see the entire Frank range and every Wi-Fi router in the 5 gigahertz band, there's just a tremendous amount of noise. So being able to run that in the ham band makes a huge difference. With a radio like this, I think our longest shot is 75 miles. So having a couple of these on both ends, you get a signal on the order of about minus 50, minus 60 dBm, and so you still have a pretty good throughput throughout the system. As you can imagine, at those long distances, picking one of these is kind of a chore. So there's actually on the mounting hardware in the back here, some fine adjustments so that you can actually move it in very small increments, which really helps to actually get the link up properly peaked, both in the horizontal and the vertical. And obviously, as you can tell from the polarization here, these are actually dual polarization radios. So they have 2 channels that are at 90 degrees to each other, and the antenna also supports that cross polarization, so that you actually have the 2 channels, and the radio is smart enough to know that it talks on this channel versus that channel. With the other radio, it automatically syncs that up. The other issue with this, of course, is that when you're going these really long distances, the time of flight get up in the millisecond range, right? So the speed of light is round about 6 miles per microsecond. And so if you've got a 60-mile shot, that's 10 microseconds just to get over there and 10 microseconds just to get back, plus whatever delay there is in the radio. So these radios actually have a variation on the standard 802.11 protocol called in-stream that is specifically geared towards having these very long times of flight. And so it actually opens up the retransmit window quite a bit, so that it can deal with the fact that it may take quite a long time to get the signal over there and back. And of course, there's all kinds of things built into the protocol for retransmit and all of that kind of stuff to deal with collisions and just flutter and noise and whatever. The key thing, though, of course, if you're in the 5 gigahertz band and the 60 gigahertz band, even more so, is it's got to be line of sight. There can't be anything in the middle. Even a little bit of trees in the middle will cause all kinds of problems. And in the 60 gigahertz band, it is subject to rain fade. So, of course, in the 60 gigahertz band, we have much more bandwidth per channel, so you can put a lot more through a particular on one of the channels. The rain fade is a bit of a problem. It's not super sensitive to it, but if you have a really big thunderstorm, you will probably lose the signal at 60 gigahertz. But you can get a gigabit through there. On 5 gigahertz, we're typically talking about 60 to 100 megabits per second on a good path. So here's a picture of the network. This one is a little bit dated, but essentially what we're trying to do is to create as many loops in the network as we can. So if you look at these, the purple wires are the microwave links. The red wires is where we have commercial IP backup to this. So the idea is, for example, let's say we have a long string of radios going from the Front Range to Grand Junction. At this time, we don't have another way from Grand Junction back to the Front Range. So we have commercial IP on the far end, so that if you lose something in the middle, you can sort of go around the long way and come back. In most other places, we actually have microwave more than one way into the same site. So if you look at some of these patterns here, you'll see that we basically go from, let's say, Devil's Head out to Badger to Cripple Creek and back to El Magre, and then from El Magre back to Devil's Head, right? So we've got so that you can get to the site both ways. But that also means you send a packet one way and that same packet arrives back at the origin, right? So you've got packets going around and around and around. You don't want that to happen. So in order to properly configure a network such as this, you need some sort of a protocol that decides how traffic goes, and we employ OSPF for that. OSPF stands for the Open Shortest Path First, and the network is a completely routed network. That essentially means that traffic never leaves a site unless there's a deliberate decision to send it across one of the microwave links. And so the way that the sites are set up is that they have a local subnet that all of the equipment is connected to. And then there's a site router that then decides how traffic should go to the various locations. Each of those routers run OSPF. And basically what OSPF does is it finds the shortest route based on a weighting to get to each of the other sites. And so the OSPF system is, scales well enough to deal with the number of sites that we have, about 250 of them, but it's also very fast. So there are other protocols like BGP that sort of runs the internet as a whole, but that is a much slower protocol to actually find a new path. On a busy site, it could sometimes take several minutes to do that. With OSPF, typically it takes it only about 5 or 6 seconds to actually change the routing from any site to any other site as soon as it detects that there's a problem. The other problem with a complex network like this, of course, is that because there is some built-in redundancy, things break and you don't know that they've broken till something else breaks and now you've got a problem. So built into all of our networking operations is some monitoring. So the thing that you see over here, get the microphone out of the way. With all the blue on it, blue means good. It essentially is, so this wire here connects to this Raspberry Pi over here, and this Raspberry Pi runs a program called CPing. So what CPing does is it sends a packet to each of the routers on the board here once per second, records the round trip time, and the round trip times here, because everything is locally connected, are all in the single millisecond range, right? So there's a number associated with all of those, typically a 1 or a 2, that says it took 1 millisecond to get there and back. Of course, in the real network, we have round trip times of the order of about 10 to 20 milliseconds. So it takes a little bit longer, but you still want to see blue everywhere. And of course, if something fails, what it will do is it'll put a red X to show that it can't actually get a packet through, or what it will show is whatever the round trip time is. Where that becomes really important is that all of our repeater linking, of course, is based on essentially VoIP, right? So especially like P25 systems are very intolerant of jitter. So if you're running a VoIP system where the travel time between one site and the other is of the order of, let's say, 100 milliseconds, you can simply set up a buffer that's wide enough to actually deal with that kind of delay. And so, how you'll hear that is, you key up on the connection, you say, hey, this is ACØKQ, you unkey, and half a second later, you hear yourself, right? So it went to the main site, retransmitted it from there, and then you hear that. So you can buffer for that kind of jitter. On the other end, P25 systems were designed to actually use telephone lines where there's very little delay. That's at least the version 1 of ACØKQ. And so one of the things that we specifically use this is to detect the jitter in the system. So sometimes the packet takes 5 milliseconds, sometimes it takes 50 milliseconds. A lot of these VoIP systems do not like that. You have all kinds of stutter and the audio doesn't sound good. The digital systems tend to be much more robust in that because they were built inherently for IP connections, which have jitter like in any packet switch network. But on this screen, if you see lots of blue but some yellows and greens mixed in there, that means that you've got a lot of jitter and there's something that you need to resolve. But so what you'll see there is all just a bunch of blue that shows that it can get to any particular site. And I can go into any of those and say, well, how do you actually get there? But what I'll show you first is, well, what happens if I break something? So if I actually disconnect the link between Saddleback and Squaw, you'll see that there was a little red line that came through there. And for a few milliseconds, or actually 1 millisecond, it was unable to get to all of the things down here on the south. But it very rapidly recognized that that link is down, routed around it, and reestablished the connection to all of the others, right? So that's the nice thing about OSPF. It's really fast in terms of doing that. And if you had just an audio blip for 1 second, that's probably not that big a deal. It's probably too small for you to see, so I'm not gonna, come on. Yeah, I'm not gonna bother trying to show you the actual path it got to go there. But then if I were to reestablish that connection, it'll take a few seconds to realize, oh, there's actually now a shorter path to get to that same site. And then it will start sending the traffic back through the regular path. And the way that you'll see that is instead of there being green in here, which indicates a travel time in the order of about 10 milliseconds or so, everything has gone back to blue, which basically means that you've got much faster transmissions. And so that's sort of the overall behavior of the system in terms of healing itself. And so when we design the network, we specifically build it with these loops in mind. So, for example, going out east, we've got a link going from Saddleback to Guy Hill to Burlington, and we're trying to connect that down to the Arkansas and come back along the Arkansas. So we have a big loop that way to connect that around. And the same thing for the western slope. Right now, we're out to Waterdog Mountain, which is near delta and trying to build another big loop down from the southern end through the San Luis Valley and back connecting to the system. And we got a grant from ARDC to actually employ all of these new sites. The key thing in RMHAM, though, is that we're looking for cooperators, right? So we always say we're not an ISP. So we're not going to just come into your site and provide you with internet access. What we want is a cooperating agreement where, you'll provide the site, you'll provide a repeater at that site, you'll provide, something of value to the ham community. And, by us bringing IP to that site and allowing you to connect to the rest of the world, we make it better for everybody, plus provide that public safety backup for everyone. So the other thing, and that's kind of what I was talking about. Just as an example, to get over to Grand Junction, we go from Badger Mountain to Mosquito Pass. Really difficult site. It's solar powered and it's a bear to get to. Upper Dowd, which is just by Vale, Bellyache, which is west about 8 miles, Castle Peak, Sunshine Peak, which is near Glenwood Springs, and then Palisade Point right above Grand Junction. So you'll see there's many hops in all of those links to be able to go point to point. But we have these wonderful tall towers called mountains where we can put stuff and go pretty long shots. So for example, Sunshine to Palisades, like a 50-mile shot. So you can go quite a long way away compared to, out in the Midwest. Going out on the Eastern Plains, we need to be friends with people with really tall towers so we can go any significant distance. I said all of that. So OSPF, the open shortest path first, is kind of the important way to actually connect everything together. It's very fast and very reliable, but it is very intolerant of flaky links. So if you have a lot of noise on a link, or you have high packet loss on a link, OSPF doesn't work really well in that particular environment. So we try to not have really messy links in that sense. In order, let me sit down. In order to make sure that everything stays up, what we actually do is run a tool. Oh, by the way, since there's activity on the Colorado connection right now, let me do this out of order. One of the big things that we can get out of this linked repeater system is the ability to link an arbitrary set of sites together that run the same protocol. So the Colorado connection is largely based on All-Star Link, which is a radio-to-radio, analog radio-to-radio connection system. And this particular piece of software, it's called Callmon. It's a way to monitor those kind of networks. It's a hierarchical system. So the Colorado connection has one, the CRA has one. So you can kind of see this is the CRA machines. This is the Colorado connection. And as soon as there's activity somewhere on the network, somebody keys up, what it shows us is right now, the Thoroton voter is the receiver that's causing the audio. This is a voted receiver system. So it shows you the signal strength for all of those. The one that's shown in green is the one that is actually being retransmitted. The ones that are in blue are the ones that are potentials for retransmit. And then it also shows you just the status of everything else. So all of these other radios are transmitting. It says link here. You can probably not read it that far. But basically what it means is that it's transmitting audio from the link, whereas this one here is transmitting local audio because it's just in a regular repeat mode. And you can kind of see what the activity on the system is. At the same time, I've got the CRA up here. you'll see that the Cheyenne Mountain radio, right, or the Cheyenne Mountain site actually is completely down right now. For at least for CRA, they've had some equipment failure, so it shows no data. But if somebody were to key up on, for example, the 145, you'll see the signal come up and how it's being retransmitted and connected to that. The nice thing about this particular system is that, let's say we have something like the SantaNet or an emergency of whatever kind, and we now actually want to reconfigure the system. So instead of just using the Colorado connection as it's currently configured, we want to take, let's say, the Floridan repeater, tie it in with the NCARC machine on Buckhorn, and the 145 of the CRA. Through this particular tool, we can actually disconnect them from the rest of the system and form a new ad hoc cluster of repeaters that are then tied together. And because this particular tool has all of the different clubs and stuff represented in it, you're not restricted to just doing one club at a time. You can actually have any of the repeaters that support this technology linked together in the system. Now, of course, that's something that you can do with any All-Star link, right? As long as you have a public address that you can go to. However, in this case, these are all private nodes. So this particular tool has a way of aggregating all of that information and basically allow you to do those kinds of private connections that otherwise you would have to do a lot of manual messing around in order to actually do that. But this is also an invaluable tool for a system as big as ours to see if there's noise on the system. Where is it coming from? We can go into each of the, or basically look at that, see what they are, and once I log in, I can actually go and mute any of the repeaters or dislink them or whatever controls we need to do with those. So just a little bit of a distraction there. But the part that I wanted to show you was how we actually monitor the network. So if you look at all of the green there on the map of the United States, that's basically the coverage provided by our network. We do not have a site in Atlanta. I've yelled at Jeff a dozen times about that. But basically all of these connections here are individual sites. And of course, you know, if you have almost 1,000 devices on the network, you can expect that one of them are going to break every day. So the goal here is to actually monitor this. You'll see there's a little bit of red that's covered up by something, but it'll basically send us an alert on our phone as well as by email that says, hey, something broke or something, you know, is not acting the way it should. But this particular tool basically polls everything on the network every 10 minutes and gets its status and its CPU usage, the usage on all of the links, all of that kind of stuff, to basically just monitor the behavior of the system. The other very useful tool here is called SmokePing. So what SmokePing does, sorry. Why is it not? Oh, I didn't set up DNS correctly. Oh, never mind. I'll show you a picture of what it's supposed to. Oh, there it came. What this actually does is it measures the quality of that link over a longer period of time. So if we pick, for example, the West Creek site, what it shows you is over the last 3 hours, over the last 30 hours, over the last 10 days, and over the last 360 days, how the network was behaving. So one of the big things, of course, is if you're troubleshooting a system is well, what is it supposed to be doing, right? So in this case, you can see that for a while here, we had a pretty solid link. Then for a while here, we had this sort of bluish color, right? That means we were losing roughly 5% of the packets. So something was wrong that, took a long time to recover. Well, it was because we were on Starlink for a while because we had lost the microwave. And then, it basically came back here on microwave later on. And you can basically look at the historical pattern and compare things to how they used to behave versus how they currently should behave. And then, of course, what this does is to measure it, CPING does, is to measure things at a much shorter time interval to actually measure all of the, things like jitter on a very fine-grained scale so that you can deal with things like the jitter that you get out of, or messes up the P25 systems and so forth. So the long and the short of this, all of this monitoring and control is really what makes the system as reliable as it has been. We haven't had an outage of the network in at least 5 years. But of course, the problem with all of this is that it is very susceptible to lightning, right? So if you have to take a big lightning strike at a site, you got a problem. So this is our workhorse router that we have at most of the sites. It's a MikroTik RB2011. Costs about $100, so it's not an expensive device. However, the signals that you get for IP are on the 1 or 2 volt range, right? So if lightning suddenly puts 50 or 100 volts into one of those ports, it does not survive. Fortunately, our experience has been with this kind of device that it usually blows out the port itself, but not the entire device. So as long as it's a single strike, that's not too bad. So what we typically do with other devices such as this is it has an SFP cage in the back. So we can actually run fiber from the router. And you'll see that this has an SFP cage in here. This one has only one, but you can get these with 10 SFP cages and then basically run fiber from the radio to the router and then just provide power through the VoIP port or the PoE port to actually power the radio. These kinds of things are relatively inexpensive, I should say. Setting up one of these, you're talking about $500 for each end of the shot. The microwave radio is about $200, and then the dish is another couple of $100, and then, the fiber and everything else. So how would you set up one of these for yourself, right? So what we have is obviously some long-range links. And, for that, you need one of those 2-watt radios. There's also some other devices that we use for shorter shots. So what we have here is what's called an LHG, light head grid. It's also a 5 gigahertz device. And you'll see this one is labeled US, so somebody bought this by accident. So don't take this to a mountaintop. It won't run in the ham band. But essentially, all of the electronics are just built into this little front here. It's got a metal reflector in the back to give you like a 25 dB gain on the antenna. But you basically just feed it through an Ethernet cable. You provide power over Ethernet at the far end with one of these injectors, and this will then plug into your device. And so there's a couple that I have here. This is called a QRT. This has a range of somewhere in the range of about 6 or 8 miles or so. It's a 200 milliwatt radio, if I remember correctly. This is a 100 milliwatt radio. You can see that the construction on this is mostly plastic. But we've been very surprised at just how well this stands up to being out in the weather. These are a little bit more robust. I have one at the very top of my tower with one of these that goes out to Strasbourg. It's been up there for several years now. Never had any problem with those. So even though the case is, of course, plastic, it's actually a pretty solid construction internally with, a metal backbone. So you'll see that they come with all kinds of nice things to actually configure them. So right now, you'll see there's a lot of green lights being shown here. That's because this radio is talking to that radio. So obviously not much of a challenge there. But this is very convenient for actually peaking the link. You can just use the lights there to do approximate peaking, both in element and elevation. And then you can actually switch to the software and fine tune it to actually get the best overall link to it. The nice thing about something like this is that it's IP in and IP out. So if I had more time, what I would have demonstrated is that I can actually pull one of these purple wires out and plug those two radios, one on this side, one on that side. And it's basically just a bridge between those two by RF. So it's a great way of accessing a remote site. And of course, if you have one of those, you can set up a much longer range links for that. The last device I wanted to show you was this one. So this is what we use at sites like Thorndon and Almagre, where we have a lot of concentration coming in from these commercial links, or it's just a site that takes a lot of traffic. So this is a little bit more expensive router. It's about $500. But the same thing from Cisco will probably cost you about 10 grand. It's got a pretty fast switch in it. And the nice thing is that all of these ports can do any function. It's not like your home router where there's an internet port and then all of your local LAN ports. All of these can basically be an internet port, and you just need to configure them appropriately to actually set up routing for each of those. And with something like OSPF, all you have to do is to say what's on the other side, and it'll figure out how to actually get from a site down here to a site up there in the best possible way. So I'm told my time's up. Okay.
Grab your microphone. All right. Thanks, Willem. That was awesome.
Any questions?
So what's the cost of those smaller units?
Question was, what was the cost for the small units? Here.
The QRT is about $100 or thereabouts, a little over $100. The LHGs, last I looked, was $75. It's basically, it comes with, you put IP in and goes microwave out. Everything is self-contained. The other thing that's very nice about the MikroTik series of equipment is the same operating system that runs the radio is also the operating system that runs the router. So if you're familiar with the one, you can do the other, and there's just one more drop down that deals with setting the microwave frequency and channels.
What's your typical bandwidth and round trip?
So the bandwidth is typically on the order of about 30 to 60 megabits per second. Since we're mostly moving audio traffic, that's plenty. Where we sometimes saturate the link is if we run a lot of video. So at most of the sites, we have security cameras. And when they trigger, they can put, 10 megabits per camera on the link. And you have a lot of those. You can saturate the link.
That's nice. Freaking Microsoft products.
But that's really.
Correct. So we do run SSH over these links because that's how you control these. So I'm using the command and control exception to do that. But everything else we run is unencrypted. So from Thornton to Grand Junction, I believe is 17 milliseconds. 17. So it's pretty fast.
Yeah.
What's the most signal rotation? You said that those would switch horizontally vertically. Is each one separate, and how much rotation do you get to transmitting, say, from Florida horizontally, and then you go out to the other side? Will you get rotation, so it'll be vertical?
I think it's
And which Florida is that continuously switching to see which is best?
Yeah, so it actually runs both simultaneously. So the radio actually has two channels, and the one goes horizontal and one vertical. And on the other side, it figures out which channel is which channel. So if it was exactly 90 degrees, it could figure it out, or no rotation, it could figure it out. But we try to keep the paths as clean as we can so that you don't have a lot of rotational problems. If you get into the Fresnel zone, all bets are off. No, since we only use use it as an emergency in an emergency, I think we have an exception to use it for that purpose. So where we have only commercial IP access, like Akron, for example, we don't actually have a microwave link into Akron yet. So there we have two VPN links that go out from Akron, from Akron, one to Thornton and one to El Magre. So if El Magre is down for some reason, we fail over to Thornton, otherwise the other way around. But that internet connection on the far end is the single point of failure. If that's down, we have no way of talking. So at Akron, for a while, we actually had a microwave link to another site that we had VPNs from. But, those sites out there, we're still building the microwave network out there. We don't have direct connection for all of those. A lot of the ones that showed as POP originally are now microwave connected.